But let's just launch off. Welcome to the 19 April meeting of the San Diego Astronomy Association. I'm Steve Hallman, Vice President of the SDAA and your host for the evening. And I want to start you off with a little video. Many of you may know the Ingenuity helicopter on the Mars Perseverance rover actually flew either yesterday or today, and here's a little video on it.
This month, NASA's 4-pound Ingenuity helicopter separated from the belly of the Perseverance rover. A day later, the rover backed up to allow the helicopter's solar array to charge and sent this picture back to Earth.
If this flight is successful, I think it is a transformative event for planetary exploration.
This is a model of NASA's Ingenuity helicopter. In just a few days, a duplicate of this craft will attempt something never done before: flight on Mars.
Applicant indicates chute deployed.
We have confirmation that the lander vision system has produced a valid solution.
Ingenuity was carried to Mars by NASA's Perseverance rover,
Touchdown confirmed.
which landed on the red planet on February 18th after a 7-month, 293 million-mile voyage from Earth. Since touching down on the Martian surface, Perseverance has been snapping pictures and analyzing nearby rocks. But perhaps the most anticipated part of the rover's mission is still to take place: the flight of its Martian helicopter, Ingenuity.
So Ingenuity was designed as a tech demo to show that aerial robotics like this are able to be used for planetary exploration.
Ben Peipenberg is a senior aeromechanical engineer at AeroVironment, the contractor hired by NASA to build the aircraft.
Right now we're in AeroVironment's clean room facility. I've personally spent thousands of man hours in this room. And this is the facility that we built a lot of the flight hardware that's currently on Ingenuity. It's actually on Mars.
For the past 7 years, Peipenberg has been working on making Ingenuity a reality.
So that 7-year development process involved a lot of fabrication. So taking all of the raw components, turning that into molded parts. And so, for example, using these kinds of carbon fiber materials and molding that to develop the rotor blades on Ingenuity.
Engineering something like this for an environment that we've never actually flown in before is very challenging. There have been a lot of other space probes and missions that have gone to Mars, and so we have some understanding of the environment. However, nobody's ever flown on Mars before.
What we do know about the Martian environment suggests that flight as we know it would be difficult.
The Martian atmosphere is much thinner than Earth's atmosphere. It's very similar to Earth at about 100,000 feet, actually.
NASA and AeroVironment had the challenge of designing a craft without being able to test in the environment in which it would fly.
A lot of the testing that happened on the Mars helicopter happened at JPL's Space Simulator facility. It's a very large vacuum chamber that can be filled with CO2 gas to simulate the atmosphere on Mars. You know, it's a really special facility. There are very few like that in the world.
To make Ingenuity a reality, NASA looked to a small defense contractor, AeroVironment, that specializes in unmanned aerial vehicles.
So right now we're in AeroVironment's Nano Air Vehicle Lab. And this is a research and development space. And actually a lot of the products that have come out of AeroVironment have started in this lab. So this was one of the first helicopters that we actually built and flew in the space simulator at JPL. This was just a very simple model. It was attempting to demonstrate free flight in a Martian atmosphere. And it was the first helicopter that actually did that. This is one of the very early rotor blade designs that was tested. The engineering data that was generated from testing this prototype fed directly into the development of the final rotor blade system on Ingenuity.
Ben Peipenberg played a major part in designing and building the high-speed counter-rotating helicopter blades.
The rotor blades on Ingenuity are designed from composite materials, so it's carbon fiber over an engineering foam material They're very, very lightweight and they're very rigid, and that's required to control the helicopter and to make the whole thing light enough to be able to fly.
For its maiden flight, the 4-pound craft will rise 10 feet above the surface.
So this flight will be less than a minute likely, and it'll be roughly 1 story off the ground. So very simple, very benign, low risk to the hardware. And the whole point here is just to demonstrate that this is possible and generate the engineering data that we need to move on to the more capable, more exciting flights.
NASA officials have likened Ingenuity to the Wright brothers' Flyer, which in 1903 made the first controlled powered flight on Earth, a 12-second, 120-foot trip. In homage to that flight, Ingenuity carries with it a swatch of fabric from the Flyer on the underside of its solar panels. NASA says it plans to conduct up to 5 additional flights over the next month. These future flights will test the helicopter's ability to fly higher and longer. Meanwhile, the Perseverance rover will be nearby, observing and recording the historic flights.
All right, Mike, if you can give me the next chart. So I thought that was really cool. I would encourage you all to take a look at the news and watch on the Perseverance rover and the Ingenuity helicopter. So just to take an opportunity to remind you all, the San Diego Astronomy Association has a website, SDAA.org. You can type in SDAA.org into Google and we're the first thing that comes up. And on there, on the website, we have a number of things for supporting astronomy in our community, including a loaner program for telescopes. So if you would like to join our organization, you can borrow a telescope we have. You can try it out. And Mike, there's a link to the webpage where we do loaner scopes. If you could put that link in the chat, thank you, go back one chart and pull that link and put it into the chat, that would be good.
Will do, Steve.
Okay. And so you can just copy that link and put it into the address bar on your browser, and it'll take you directly to the web page on our web, or on our web page you can actually look at what scopes we have and put in to get a loaner for 3 months. If you don't have a scope, you're new to astronomy, or if you'd like to try out a new kind of scope you don't have, I encourage you to do that. I also mentioned that we have Facebook, Twitter, and Instagram accounts, so you can go sign up to them, and we post information about our public outreach events as well as our various meetings that we're having. In addition to that, we have a newsletter that we put out, and in the April issue of the newsletter, we have an article called Watching the Lion, Celestial Wonders of the Constellation Leo. So you can go take a look at that and read about what's coming up in the constellation Leo that you could take your telescope out and take a look at. So, and also, if Mike, you could put the link to that in the chat. So there's the scope loaner program link. So if you just copy that from the chat, you can go take a look at what scopes we have, and there's the link to this month's newsletter, which is free. So please go take a look at that. It contains information about the club business as well as information on just general astronomy stuff. So Mike, if you can take us back to my charts and advance us to the next chart. Yeah, so I'll just mention to everyone that we have a YouTube channel. So all of our program meetings are put up on the YouTube channel, and we also do public outreach on our YouTube channel. We have currently over 450 subscribers, 74,000 views on our YouTube channel. So if you miss one of our meetings, you can go back and watch it, or if something went by a little too fast for you in the meeting and you wanted to go back and take a look at it, you can do that. Also, our community events, we live stream them and record them and put them up on YouTube for you. So I would encourage you to take a look at say a great article or a great one of our more recent postings on our YouTube channel, which is our featured outreach event saying goodbye to winter. So of course you all understand doing outreach events to the public is challenging and in COVID circumstances, but we're finding new and creative ways to do just that. So if you would take me to the next chart, I just wanted to mention for our club members that May 15th, we're going to have our annual cleanup at our dark site. So for those of you who don't know, the club has a location out the 8 freeway about halfway to the Arizona border, where you can bring your telescope and set it up in dark skies and observe under reasonably good conditions, not like in the city of San Diego. Any of you who are interested in doing that, you could contact Jerry Hilburn. We're going to have a dumpster out there for cleanup. A number of members already have pads out there, so this is your chance to clean up your pad and get rid of stuff that you didn't want. And we encourage you to bring your weed whackers and yard tools and stuff like that to pick up and help clean up our site that we maintain for the benefit of the club, and we have public events out there also. So, and there you see that link right there is that just popped up in the chat will take you to the part of our website where you can get more information on this activity if you're interested in going out, pitching in a little and helping clean up our site, for keeping it clean and pristine for the public and for all of our astronomical members to enjoy. So next chart, we have another video. I wanted to pass this one on, and I believe the SpaceX program just won a multi-billion-dollar contract to build a lander on the moon, and a variant of their Starship, which is what this video is about. One of the tests of this type of Starship is what they're planning to fly to and transport astronauts and the return to the moon. So Mike, if you'll play the video.
3, 2, 1, ignition. We got liftoff.
So I'll just make a few points about that video. you saw it take off vertically, which is how it will take off from the Earth, and then it turned horizontally. When this craft actually plans on returning to the Earth, it actually turns horizontally and plows through the atmosphere like that, dissipating speed in this kind of laying down position. And that's why it has kind of like little winglets on the side to maneuver it. And then when it gets near the surface of the Earth, it will actually turn its engine back on and reorient itself to the vertical position before landing upright. It's a total new concept in takeoff and landing. And I think it's going to be really impressive to watch them go through that. This spacecraft, a variant of it, is also intended to fly astronauts to Mars in SpaceX's plan. So I thought, and use that kind of maneuver of lying down in the Martian atmosphere to slow itself down and land on the planet. So if you can take me to the next chart. There you go. So this is now it's time to, I'm going to give out what we call the digital door prize. So I searched for something that's kind of cool that you might like, that's free, that we give out to everyone who comes to our meeting. And so in this case, if you will paste the link to this into the chat, and I would like you all to, if you're interested in this, to copy that link and save it in your browser. Because that link will take you to the website you see here in the window, which maintains a current list of what the brightest supernova is. And when I cut this or shot this off the page a few days ago, the brightest supernova was not super bright, it was at 13.3 magnitude, but it gives you a link where you can go directly to what object in the sky that's in. So if you're interested maybe in watching for supernovas to pop up, occasionally they get quite bright if they're in a galaxy nearby, and so that's kind of a cool thing to do. And so your gift for attending tonight, your door prize, is a website that you can monitor for watching supernova go off. And so this is actually done for the astronomical community. The professional astronomical community uses it, as well as the amateur community. And so you can go there and just, when you're planning your observing session on a night, you can go see, is there some maybe cool supernova you'd like to snap a picture of, and add that to your collection for the evening. And so now, if you'll take me to our next slide, I would like to introduce Dr. Eric Sandquist of San Diego State University's Astronomy Department, who will introduce the Lucas Scholarship Award winners.
So thank you for inviting us, and I'm happy to be here on behalf of the Astronomy Department at San Diego State, and especially to thank you for your continuing support of the Lucas Scholarship. And of course, we wanted to show some of the wonderful results that come out of this scholarship at San Diego State. So we're going to do a kind of science equivalent of speed dating here by having 5 of our Lucas Scholarship Award winners tell you briefly about their research and their future plans. And we're going to go a little bit out of order that you just saw. We're going to go sort of from small and near to big and as far as you can go. But it's all going to be very exciting stuff. So we're going to start with one of our graduate students, Josiah Purdom.
Thank you, Dr. Sandquist. So I'm going to share my screen. I have a visual aid. So let's see. Hopefully I share the right one. Yeah, okay. So, that doesn't look right. So sorry, technical difficulties. Okay. So let me go ahead and get this started. Okay, so I'm researching an asteroid. Well, it's called an active asteroid. Its name is 6478 Gault. Basically, it just grew some tails like a comet back in 2019, late 2018, early 2019. So here are a couple images of it with a couple of tails. If you're wondering what's going on in the image, these streaking objects are stars. We stacked a bunch of images using what's called non-sidereal tracking. Probably a lot of you know what that is. And so we kind of set out to find out why it grew these tails back then. Some people thought they had an idea, but nobody really could confirm exactly why it had tails. And so me and a few other astronomers all over the world actually took some long period observations. So what we're seeing here at the top graph is basically its brightness over time. So we want to look for any kind of rotation in its brightness. So if it's rotating too fast or something like that, that could be why it's breaking up. So you don't really see a huge rotation. You see it kind of as a flat line, but there are these kind of peaks, and you see these peaks happen every 2.5 hours. And so I took this light curve from everyone and I divided the light curve by 2.5 hours. And so that's what this light curve down here is. It's called a phase folded light curve. Basically, I see that it peaks here and then it peaks again. And that's what we expect from asteroids, is we see a double peaked rotation. So basically, sometimes they're not exact like ball looking things, but they have a kind of a little bit of football shape. So if it's spinning like this, you'll see it get point and then big and then point and then big, and that's why we see a double peak. But because it's so flat, we actually do think it's semi-spherical, kind of what's called top-shaped. So like Bennu, if you remember the OSIRIS-REx mission from last year, where they gathered the asteroid samples and then jetted off and are coming back home, we expect it to look like Bennu. And with the shape that it has and the kind of density that it has, it's rotating about 2.5 hours. That's what exactly we expect the critical rotation to be. So that means that it's spinning too fast, and now it's breaking up, and that's why the tails are happening, because landslides are happening on those. So I do want to thank the San Diego Astronomy Association and all the donors for the William F. Lucas endowment. So that's all mine.
Thank you.
Thank you, Josiah. So we're going to move away from crazy things in the solar system to stars. So first, we're going to have graduate student Alex Dimoff.
Hi there. I'm going to do the whole presentation thing as well and share my screen here. So here we go. Go to this guy. All right. Hopefully this thing isn't too big and in the way. So hello, I'm Alex, and I'm here to talk to you a little bit about my research, a new method to determine the internal structure constants of eclipsing binary stars. I'm, like Dr. Sanquist said, I'm a second-year master's student, and Dr. Oros is my research advisor. So what I'm actually doing is using ELC, which is a computer program written by Dr. Oros. And what it does is it solves the Newtonian equations of motion. So Newton came up with some equations in calculus that can describe the orbit of two bodies in a binary system. But as it turns out, real objects aren't perfectly circular orbits. There's perturbations from relativity, tidal forces, rotation of the stars. And so as it turns out, these orbits are more elliptical, and they're not actually closed either. They're open. So you can see over here on the bottom right side, there's this spirograph shape. And that's more of what orbits look like over very long periods of time. And so apsidal motion is that rotation of the orbit, and that's what we're searching for here across these 5 binary systems that I have listed. And these internal structure constants tell us about what's going on inside the star, and we can use them to help calibrate stellar evolution models. And so that's pretty exciting. Some other exciting components of this research is the running the code takes quite a long time. And so we implement parallel computing methods on various different machines. And we've been able to use the supercomputer EMI in Germany, which is the 47th fastest in the world. So that's pretty exciting, pretty cool. I'm happy about that. And some preliminary results show that the algorithm succeeds well in determining the physical parameters of the system, so we can get the masses and the radii of these stars. But the individual apsidal constants, there's still a little bit of trouble, so I'm running some other simulations in the background right now to try and figure out what's going on. but we can get the average of those two constants pretty precisely. So that's wonderful. And the last thing I want to show you is just this pretty cool plot. So what we're looking at here are sets of eclipse times. So you watch an eclipsing binary and you mark down the times that it eclipses. And if you have a perfectly circular system, you expect there to just be pretty much a flat line across 0. But we see these really cool sinusoidal shapes. And we fit these solid lines to them. And this is the apsidal motion of that binary orbit. The sinusoidal shape is the rotation of the orbit. And so there's also a third curve kind of hidden behind these. You can kind of see it peak at 1940 and then over here at about 2010 or so. And that means there's a third body in the system adding another perturbation there. So big thank you to San Diego Astronomy Association for the Lucas Endowment. You guys have been really helpful in actually producing this plot right here. I did that with some computer parts that I was able to purchase. So thank you guys so much. Very exciting, very cool.
Our pleasure. Thank you.
I should mention that both Josiah and Alex, I think, are going to be defending their theses within the next couple of weeks. And then our third student, Rex Lamb, is going to be defending sometime soon after that. Rex
luck.
is also a graduate student, and he's going to be talking about stars as well.
So,
Can you maybe- oh, sorry, yeah. Turn up your mic a little bit.
Turn up my mic.
You're
Can you hear me?
You're good now.
Good. I don't think I did anything, but okay.
Just speak up.
Okay, all right. Can you all see that?
Yes.
Fantastic, great. Okay, so I'm working with binaries, similar to Alex, but looking at a slightly different kind of part about the binary, specifically its mass and ages. So if we look at clusters specifically, what we find is that clusters tend to have what we call a turnoff point. So these are two different clusters, which has M67 and NGC 188. And what we can do is basically look at what we call the HR diagram and figure out where exactly these stars kind of evolve off of the main sequence. The main sequence being this nice little line right here. And so these stars tend to evolve off at a certain time, and these yellow stars evolve off at a different time. And what happens is that by measuring that sort of turnoff point, we can kind of measure exactly how old these stars tend to be in the cluster. And since the cluster tends to birth these stars at roughly the same time, we get a sense of the age of the entire cluster. And so this is something that I'm trying to work on with my own cluster. So I'm working on a cluster known as Coma Berenices. Now, Coma Berenices doesn't have as many stars as some of these bigger clusters, or at least not as much resolvable stars. So what we find is that the HR diagram for that same sort of cluster ends up looking a little bit more sparse than we see up here. And so when we're trying to measure the turnoff point, for example, we're basically limited to only a few points at the turnoff point. So to do that, we have to measure basically where that specific turnoff point is. And we do that using age models called isochrones. Isochrones being a bunch of different ages that we basically overplot on top of this using specific parameters from the cluster to basically pinpoint exactly what age this cluster is. Which means that this particular point and these particular points over here tend to have a lot of importance in the determination of ages of the cluster, because this happens to be roughly where the turnoff point is. So my thesis is focused on figuring out exactly where those points end up lying. I'm specifically working with 12 Coma, which happens to be one of the more massive stars in the cluster, and it basically provides a fantastic constraint for us to figure out what the ages and other very useful parameters of the entire cluster would be. Exactly. So again, thank you for everyone for all the help. It's very much appreciated. And I'm just leaving you with a nice little picture of the cluster itself and the specific binary that I'm working with here, 12 Coma. Thank you.
Thank you.
So I do want to emphasize that the Lucas Scholarship supports graduate students, but also undergraduate students. And the next two students that are going to be presenting for you are both undergraduates. The next one who's working on STARS is Madeline Overton.
Hello, yes, I'm Madeline Overton, and let me get my visual aid up. So yeah, I am a third-year student at SDSU, and I'm working with Dr. Nola in the physics department. And so what I'm trying to do is model the internal processes that produce the lithium-7 isotope in low-mass red giant stars. And we are interested in this because in some populations of stars, we see more lithium than we expect to be there. And so the way I'm trying to model lithium is by using the MESA Stellar Evolution Code. And this is a really cool program because it's open source, it's free to the public. And so I know when I first started working on this, that it was really cool to me that a very widespread tool was open to the public, and like anybody can start looking into this. And so I'm using MESA to test out different mixing processes that are going to get lithium when it's made in the center of the star out to the outer layers where we can see it. So this upcoming summer, I'm also going to be working with some simulations, but instead of standalone stars, I'm going to be looking into galaxies. And so I'm really excited about that. And then after that, I'll be a senior and looking into graduate programs. And so that is both exciting and nerve-wracking. So thank you so much for your help on my journey to get here.
Thank you.
Yeah, Madeline, don't worry about it too much. You still got a year, and there's definitely some examples of people who have been successful in getting into graduate programs, and one of those is the next presenter, Kelsey Davis, who I think several of you in SDAA are very familiar with. She's going to be going on to a PhD program, and perhaps she'll mention that during her little talk.
Yeah, here, let me attempt to share my screen because this works about 10% of the time. Can you guys see a PowerPoint that I'm sharing?
Yep, you're good.
Great. All right, that's good news. So hi, my name's Kelsey. I study something called the epoch of reionization, which is more of a very big thing, I guess, as Dr. Sandquist kind of mentioned. It's an all-sky signal that we're looking for. And that involves a lot of work with radio telescopes. And more specifically, I can change this slide. I work with the stuff that gets in the way. So I work with bright diffuse stuff that's in the way of this thing that we want to see. Here on the left, this crazy scatter plot looking thing is actually just a bunch of different observations of this source on the sky. Each color is a different observation. And I kind of added this puzzle piece to the way we calibrate our data, where I took what was previously the best model we had of this source on the left, and I wrote code that turns it into what we see here on the right, which looks a whole lot more like something we might see on the sky. Yeah, so this is kind of what my work is concentrated on for about the past year and a half. And I'm actually planning to take this project with me to a graduate program where I'm going to hopefully dive into it a bit more. So with that, next fall, I'm planning on starting a PhD program at Brown University, where I will be getting a PhD in physics. And I also received something called a graduate research fellowship from the NSF. And what that means is when you go to a PhD program, it's very typical that they waive your tuition and they give you a salary. And what this fellowship does is it puts me in charge of that money. So I'm in charge of the tuition waiver and the salary. So I can take it wherever I want and For example, I'm not required to teach because I'm in charge of my own money. So I don't have to teach for the money since I'm bringing it with me, I guess. But yeah, I see a lot of familiar faces from Boyce Astro. So if anybody ever wants to have a conversation about graduate school, I'm on your Slack channel. So feel free to reach out to me. But yeah, that's my research and my plans.
Right on.
Thank you. All right. And with that, we want to thank our Lucas Scholarship Award students. And Mike, if you could put up my last slide. And thank Dr. Sandquist.
Thank you.